Okay, we are off to chapter 4 here, and this will be starting new exam stuff. Yeah, so our first exam coming up on Wednesday, I think. Happy Valentine's Day. Yeah, so I'll do that on Wednesday there. So this will be exam 2 stuff starting here at chapter 4. So in chapter 4, we're going to talk about atoms mostly. We're going to talk about the structure of atoms, some really important experiments to help us understand the different parts of atoms. We'll talk about atomic number, mass number, protons, electrons, and neutrons. Then I think we'll finish it up kind of talking about the periodic table in this chapter. We'll first talk a little bit about compounds and formulas for compounds. And we talked about compounds a number of times, I think, up to this point. And a reminder that a compound, right, is 2 or more atoms of different elements. And that's the key part of that, as we've talked about previously. You got to have different elements involved for it to be a compound. Remember, a molecule is really more just like a generic definition, if you want to think about that, of all you need is 2 atoms or more, and they could be the same element or different elements. But in order for them to be a compound, it does have to be 2 different elements, at least 2 different elements sort of involved. Obviously, a chemical formula expresses what types of atoms are present in a formula. And when we write our formulas, we do, as we can see there with our H2O, we do use subscripts to represent how many of those atoms that we have. And the subscript is always to the right of the element it goes with. So that would mean that we have 2 hydrogen atoms present. And pretty much in chemistry, most of the time, if you do not see a number written, it represents as there is 1 of something. So there would be basically 1 oxygen atom. Again, typically we do not write the 1 in there. So we do always use subscripts to represent how many atoms of these elements always end up to the bottom right of the symbol for that particular element. And obviously, as we've talked about a couple of times up to this point, something like water obviously is a compound because it contains hydrogen and oxygen together. And it obviously has 2 or more atoms that are present in that case. Now, when we talk about a compound, compounds always sort of contain the same relative amounts of these elements. So when we have water, it will always contain 2 hydrogen atoms for every 1 oxygen atom. And as we'll talk about, by mass, they will also have sort of the same mass ratio that is present. So when we write these formulas, again, H2O, CO2, and NH3, we do use those subscripts. So in case of carbon here, there's 1 and 2 oxygens, 1 nitrogen, and 3 hydrogens. When we do write the symbols for the formulas, as you can see on the periodic tables that we got hanging in here, usually the symbols are pretty much 1 letter or 2 letter sort of abbreviations. If it is 1 letter, it is a capital letter that you want to use. If it is a 2 letter abbreviation, the first letter is capitalized, the second one is not. So common example is if you went CO like that versus CO like this. Capital C, lowercase o is cobalt, the element, but 2 capitals here, capital C and capital O is carbon monoxide, which is obviously something very different. So in the case of carbon monoxide, we would have 1 carbon and 1 oxygen present in that particular compound. So it's really important, especially if you're somebody who maybe writes capital letters for everything. You definitely don't want to do that when you're writing formulas, especially using chemical symbols, because you're really not meaning to write. So 2 letter symbols, which a lot of them are. First letter always capitalized, second one not. And if it's a 1 letter symbol, it should always be capitalized. Let's take a look at a couple examples here. Why don't you take a couple of minutes here and come up with the proper formulas for each of these things? Okay, let's take a look and see. So for the first one, we got 6 carbon atoms. So carbon is C. And once again, we would do a subscript next to it. And we have 6 hydrogen atoms. So something like that. We have a compound that has half as many calcium as chlorine. Another way of looking at that is I have 1 calcium. I should probably have twice as much chlorine. So it looks something like that. And lastly here, we got equal numbers of sodium, which is Na, nitrogen, which is N, and 3 times as many oxygens, which is that. Give a little sodium nitrate. Thank you. Any question on any of those? I would if you Jacob? Yeah, so usually another thing we'll talk about is in most cases, especially for something like this, which is sort of like an ionic compound, it's usually the slowest, simplest number if you could reduce them down. Especially as we'll talk about, that's ionic. The last two are ionic. That's definitely usually the case in that case. Yeah. But in case of this question, technically speaking, that would be the right sort of arrangement of it. Yeah. Other questions? Okay. So again, you should get sort of an understanding of the elements. If you don't have it, obviously at some point we'll talk about naming and all that, which is really important to know. I would say, to the left, to the right, kind of the middle-ish section, there's a lot of element symbols that we definitely know. Not too much on the bottom 2 rows of the periodic table, except for uranium there, but at some point you definitely want to make sure you have an understanding of what the symbol is for a particular element. And we'll do some more as we kind of continue on. All right, so we're going to then talk about atomic theory, and we're going to really talk about the atom. We're going to talk about really sort of 3 parts to the atom, which are protons, electrons, and really neutrons. And we're going to go through some events, as I mentioned before, in terms of experiments that helped us sort of understand sort of a little bit more about these sort of particles that are within an atom, where they're located and sort of what the atom is. So as we go through some of the different experiments and stuff like that, I'll tell you kind of what you need to know or remember from those. And then, so we'll get into it here. So early on, a lot of sort of the understanding of atoms came from philosophers, and they really believed that all matter is really composed of these very small sort of indestructible particles, what they called atomos, which is sort of means uncuttable, sort of indestructible. Obviously, it's a forerunner to what we call atoms, which, as we've talked about, is sort of the basic unit of all the elements, right? So that's sort of the basic representation of each of the elements that we have. So a lot of things came very clear to sort of scientists in the 18th century as they were studying sort of the atom, that most materials are either pure substances, as we talked about, and as we talked about, it could be an element or a compound. And the idea of the law of composition means that regardless of where you have the compound or sort of get the compound from, I will always have the same sort of composition. So earlier we saw, obviously, in the case of water, we have 2 hydrogens for every 1 oxygen. And again, because really oxygen is 16 grams and there's 2 hydrogens, each are basically 1 gram each. That means for every 1 gram of hydrogen that we have in water, we'll have about 8 grams of oxygen. So that ratio as to how they come together basically always comes together. And really, whole number ratios is sort of how they are fixed together when one element and another element sort of come together. They always sort of come together in sort of a whole number sort of ratio. Regardless of where you get the water, it should always be made of that, basically. May charge you more depending on what bottle it's in, but if it's just water, it's basically the same ratio. So sort of the first sort of understanding or atomic theory that came about is Dalton's atomic theory. And you do need to know these different points we're going to talk about here. But it is a theory. So as we talked about earlier on, it is something that as time went on, some parts of it were proven to be maybe not so correct in all aspects of it. So let's talk a little about Dalton. Dalton's atomic theory and Dalton himself, he was an unusual talent for math and science. He kept records of the weather every day, so he would wake up and kind of write the weather down. Oddly, never married, but probably one of the most important things is he did like to go bowling on Thursdays, so that definitely is going to show up on the exam. So don't say like Fridays, half price Sundays or something like that. It is Thursdays. But I guess the other thing he was known for, besides the bowling on Thursdays, is he actually came up with sort of a precise sort of definition of what we call atoms, and it's again referred to as sort of Dalton's atomic theory. So let's take a look at some of the important parts of Dalton's atomic theory. One of the ideas was that elements are composed of these extremely small particles called atoms, these sort of indestructible sort of particles. He said that all atoms of a given element are identical to each other in terms of their size, their mass, and their chemical properties. He also said that basically atoms of one element will differ from atoms of another. And he said that really compounds are definitely composed of more than one element involved. And chemical reactions really only involve the rearranging of these atoms. So that's sort of the idea, as we see on the bottom there, if we might, the idea of law of conservation of mass. So when we have a chemical reaction, as we'll talk about, and we did a little bit there, I think, in the energy chapter, all that happens is basically break all the bonds and then they make new bonds on the other side. So we never change any of the atoms involved in a chemical reaction. And that's why we have the law of conservation of mass, which means, if we started with 6 carbons, we will end with 6 carbons. They may be in different things along the way, but we won't lose anything along the way. And after we're done talking here in this chapter, we'll understand why that is, as chemical bonds really only involve electrons, and why that's not important in terms of the element changing or anything like that. So a couple of things that sort of are not so correct as time went on was this idea of atoms being indestructible or can't really be changed. And in nuclear reactions, for example, you can change elements. You don't have sort of conservation of elements. So they do change from one element to the next. And really, the other thing that's really not so correct is this part of it, that all atoms of a given element are identical to each other. The existence of isotopes, as we'll talk about in this chapter, isotopes are essentially the same element, but they have different masses, which obviously, if they're the same element but have different masses, they are not identical to each other. Otherwise, they would have the same mass. So the existence of isotopes sort of disproved that. But all the other stuff is still relevant and correct. As we've talked about, compounds are definitely made up of more than one element. When we do have a chemical reaction, again, that's pretty much what happens. We just kind of rearrange everybody into new compounds on the product side. So you do need to know these points, what's sort of correct and incorrect. Any questions on that there? So this is how Dalton pictured compounds. And in this case, we have basically the same 2 elements. We have nitrogen and oxygen in all these guys here. But really what happens, depending on sort of the combination of those elements that come together, how many of each of those elements together, really they're kind of their geometrical shape as well, does give them all sort of different properties. So even though they're all sort of composed of really the same 2 things, nitrogen and oxygens, they can have very, very different properties depending on how many of those nitrogens or oxygens are present, and also how they are sort of attached to each other. And that will give them very much different sort of properties. We also see that they do come together in sort of whole number ratios. We never end up with like a half atom hanging out or anything like that, or a quarter of an atom. So they come together in the proper proportion, which usually exist as whole numbers of all those. That's why when we write a chemical formula like we just did, we never have a subscript on the bottom. That's like a decimal. It's always a whole number as you go through, because it should hold numbers for everybody when they come together. So let's talk a little bit about the structure of the atom. And based on Dalton's atomic theory, several things were really thought of. Again, the idea that the atom is that basic sort of unit of these elements that could come into chemical combination. A lot of investigation early on through the 20th century demonstrated that although atoms are really small sort of particles themselves, they have even smaller particles within them, sort of an internal structure. And those are sometimes referred to as subatomic particles. And those are our electrons, protons, and neutrons. And a reminder that, as we will talk about, protons are positively charged, electrons are negatively charged, and neutrons have no charge. So as I mentioned, we're going to go through some different sort of experiments along the way here that helped us look at sort of each of these. And as I mentioned, sort of where they end up sort of in the atom, where they are in the atom, and some different ways that we can investigate each of these things. So let's take a look here. We're going to start really with the electron, and the advantage of a lot of what scientists use to sort of explore the atom was really, as we will see, taking advantage of the idea of the opposites attract. So they used a lot of sort of radioactive sort of particles that have charges in a lot of these experiments. And some popular radioactive type of particles that we come across, there are alpha particles. That's the alpha symbol there. And these are really positively charged radioactive particles. Some experiments used was referred to as beta particles. That's the beta symbol there. And these are kind of negatively charged particles. And some experiments used were referred to as gamma rays, which is really just pure radiation, has no charge. So you could almost kind of envision that, each of these are sort of used very similar to, like, we have protons, electrons, and neutrons, right? Things that have no charge, things that have positive charges, things that have negative charges. So a lot of what they did is they took advantage of using some of these radioactive sort of particles, or just particles with charges, and taking advantage of the opposites attract, and using something like, for example, if you had an electrical field where you had like a positive and a negative side, and you can basically figure out what charge, for example, a particle stream would be based on how it sort of interacts as it goes through a electrical field. So for example, if I shot particles through this electrical field and it sort of bent upwards, that would mean that the particle should have what type of charge? Opposites attract. So it bent towards the positive, it should have a negative charge, right? And if you shot a thing of particles and it bent sort of downward towards the negative part of the electrical field, that would tell you that probably that particle is positively charged. And obviously, if you shot one and pretty much was unaffected, right, by any type of electrical field, that would tell you that it basically has no charge. So using these sort of basic sort of ideas, and it allowed really these sort of scientists to explore different aspects of the atom. We could also use, as we'll have a picture coming up, I think, as well. I could use like a magnetic field as well that has like a north pole and a south pole, sort of works similar. Will bend the positive guy one way and the negative guy the other way. So the first one that was sort of explored was the electron, and it really all came about a lot of information about the electron with the development of what is known as the CRT. And the CRT is the cathode ray tube. That's what the CRT stands for there. And the cathode ray tube is pretty much like what we see here. It has a beam of negatively charged particles, and they would head this way because we have an electrical field where this guy is positive and this guy is negative. So it would go away from the same type of charge towards the positive charge. A lot of times they'll put something on the screen here that fluoresces so you can actually see where the thing is actually hitting. And you may be familiar with a CRT. If you remember maybe older TVs, older than plasmas, like old ones these people used to have on their floor and stuff like that, has like the big back, and that type of stuff. That's a CRT type TV. Years ago, you used to call a TV repairman when it didn't work. You take the back off the TV and fix the picture tube and all that kind of stuff that was in there. These things don't have those, obviously, picture tubes in it. Or maybe you've seen an old computer monitor where it has like the big back sort of to it. And those were CRT sort of computer monitors and stuff like that. You could Google the image, I suppose, at this time. But those are CRT type tubes, and it was used a lot to explore the nature of these negatively charged particles like electrons. And basically what happened, as I mentioned, is they will have a negatively charged plate. which will basically repel those negatively charged electrons away from it towards the positive side of that sort of plate. And again, that's what they would call sort of the cathode ray, which is sort of that stream of negatively charged electrons. And obviously, as I mentioned, it would maybe hit the other side and have something that will sort of fluoresce, so you could actually sort of see it as it strikes. And here is an example of what we were just talking about, sort of using charged sort of particles in an electrical field and something like a magnetic field here. So obviously this guy bending upwards would have a positive charge. This guy going down here would have a negative charge, and this guy would have no charge coming through. And again, our electrical field and our magnetic field, North Pole and South Pole, will have sort of the same effect on any type of beam that is charged. So here is a cathode ray tube. Let's take a look at it, I think.
This is a cathode ray or Crookes tube. It produces a beam of electrons as do television sets and computer monitors. A luminescent material has been painted on part of the inner surface of the tube. It produces light when electrons strike it. The electrons originate at the cathode of the tube. The long, thin object entering the scene is a bar magnet. The position of the bright spot on the screen can be changed by moving the magnet near the beam of electrons. This process is analogous to adjusting a television picture.
Which nobody does anymore. They just, go to Costco and get another TV. Nobody calls a repairman these days. But one person that used the cathode ray tube to really explore the electrons was a guy named J.J. Thomson. And there he is staring at his cathode ray tube. And he was able to use the effects of sort of electrical field, magnetic field on this cathode ray tube to explore really the electron. And he was able to come up with, in terms of the electron, the charge to mass of an electron. So one of the important things that came out of Thomson's work was the charge to mass of an electron. And that is this number right here. And the units are coulombs per gram. Coulombs is the charge, and grams is a mass. So that is the mass to charge of an electron. And this was an important sort of understanding of the electron. And even sort of further understanding of the electron came with another really important sort of experiment. And this was one done by a guy named Millikan. And Millikan did what is referred to as the oil drop experiment. And what he basically did was he took oil and he shot it through this chamber, atomized it into little droplets that went through this little hole. And the droplet of oil would basically start to fall. And as it would fall from the friction, it would pick up a charge. And within this chamber, he had basically an electrical field. So he had kind of the positive, negative plates within there. And he was able to really adjust the electrical field in such a way that pretty much the oil droplet just kind of hung there and didn't go up, didn't go down. And so he was able to really sort of dial in the electrical field to figure out the charge on the electron. So I think that's what this is right here. So there goes the oil droplets in. It's going to start to fall, adjusting the electrical field, able to kind of get that oil droplet just to kind of hang there. And from that, another really important piece of information came about an electron, and that was the actual charge of an electron, which is this number right here. And that was the charge of an electron. So these two experiments were really major experiments in terms of the electron. If we think about sort of what happened, we have Millikan, who has the charge of an electron. We had Thomson, who had the charge to mass of an electron. And basically, if we take both of these experiments together and we take the charge of an electron and actually divide it by the charge to mass of an electron, we actually could calculate the mass of an actual electron from these two experiments by taking the numbers that they had. And if we did that and we took those two values and divided them, we would see that the mass of an electron, which is sort of the result of these two important experiments, was found to be 9.09 times 10 to the minus 28 grams. So you do need to know Millikan, oil drop experiment, sort of what was done, what came out of it, along with obviously Thomson, what he did, and what came out of it. And obviously those two experiments together allowed a pretty big piece of information in terms of the electron to be determined, which is the actual mass of an electron. By the way, 9.09 times 10 to the minus 28, that's a large or small number? It's a really small number, right? It's like 28 places to the left and add some zeros, 27 zeros. So it's a really small number in terms of the mass. Any questions so far? Okay, so obviously these were two big experiments to help us understand the electron and ultimately lead us to hopefully a better understanding of the atom. So the next sort of idea about the atom was, and eventually got to sort of protons and nucleus, was the idea that at this point, they really believed a couple things about the actual atom. They believed obviously that it contained electrons, and they also believed that it was neutral, which means if it contains these negatively charged electrons, it would also mean that the atom had to contain something that was positively charged, right? That's the only way you get to no charge, right? Or neutral. So the idea was, okay, we know that it has electrons, but there must be some type of positive component to the atom that would balance out those negatively charged electrons. And sort of the early model of the atom was actually one proposed by Thomson. And Thomson did this model of the atom where he said basically the atom is a sphere of positive charge. So this positive charge spread out all over this sphere. And within this sphere, there are electrons that are sort of embedded inside. So within here, we have negatively charged electrons. And he felt that most of the mass of the atom was the electrons. So plum pudding is like a dessert with raisins sort of dropped in there. And so that was sort of the idea. Okay, like the pudding is like the positive charge spread out all over, and the raisins sort of dropped in there, kind of like the electron sort of embedded inside the atom. And this was sort of the accepted model of the atom based on sort of the early work that was done with these experiments. It was also sort of the idea of, well, I know it's got to be some type of positive charge, so I think my positive charge is just kind of spread out all over. And a much better picture of that is something like this. Again, the blue represents the positive charge. Again, our electrons embedded inside, and that's the plum pudding model, which you do need to know what it looks like and sort of what things represent. And this was sort of the accepted model of the atom until really the next major sort of experiment came along that really helped us better understand sort of the atom. And that was an experiment that was done by Rutherford, also Geiger, like Geiger counter, if you ever use anything that's radioactive, and Marston. And that is what is referred to as the gold foil experiment. And the gold foil experiment, Rutherford basically took alpha particles. So he basically took pieces of gold foil and he took these alpha particles, which again are those radioactive, positively charged particles, and he shot alpha particles at pieces of gold foil and other metals. Now, what actually happened here is something that was very different than what they sort of expected to happen. So based off of the model we were just talking about, which is the plum pudding model where we got all this positive charge spread out, we have our electrons embedded inside. They assume, for example, that when they went and shot these alpha particles, which are these positively charged particles, at these atoms here, basically, they expected it to actually kind of go through with some deflection. And that would make sense since you're charged, it's heavy, it's moving really fast, and you're throwing it through a pudding of spread out positive charge. So it's kind of like if you had a piece of paper, for example, like this paper here and here. And if this paper here was my atom, and this entire piece of paper was all the positive charge spread out really big. And if I held this side and somebody held this other side, and we shot a pin at it, right, that was moving really fast, it probably would be able to pop through, right? But as it would come through, there would be a little bit of deflection as it kind of popped through the other side. And that's sort of what they expected to happen when they did this experiment. But when they actually did this experiment, they were kind of surprised by what actually happened. They took these alpha particles and they shot them, and pretty much most of them had no problem. It just kind of sailed right through. No big deal. Nothing happened to them. But they did see that every so often they would see these alpha particles bounce off at these really large angles, even come back at the source. So this made them think that, oh, maybe this is not so good here, this model of the atom. So let's think about what that result really tells us. First off, if I shot alpha particles and they sail through, no problem, not deflected. What'd they hit? Pretty much nothing, right? So if I took my pen and my paper wasn't in the way and I just threw it that way, it's going to go straight, right? Nothing's going to happen to it. It's not going to come in contact with anybody, as long as I don't hit the door, I suppose. But every so often, right, we have these alpha particles, which are radioactive, heavy particles moving really fast, to be bounced off at really, really large angles. And that would mean that they had to hit something that was what type of charge? Yeah, very positively charged, right? Because they're positively charged, right? So the only thing that would make them bounce off at these really large angles is they had to hit something that was very densely positively charged to bounce them off the other way. If they hit something that was negatively charged, they would just stick, right? Because they'd be attracted to it, right? So they had to hit something that was sort of positively charged. But as we'll talk about here in the next couple of slides, and we'll sort of see, they had to sort of rethink this sort of positive charge within the atom that maybe it's not really spread out all over, but maybe if we took our positive charge and we did some folding here, so like 7 times, you can't fold anymore. Is that maybe it? So we took all our positive charge instead of being all spread out. Maybe we have a really centralized, dense positive charge here. And if I took my pen and threw it at it and not missed it, let me try that again, right? It's going to actually bounce off, right? And because it's very strong there. Sorry about that. I didn't mean to throw that pen at you. Or wear goggles on the front row. You never know. So this was a really major sort of discovery in terms of the structure of the atom, and it was very surprising. And that's not what they actually thought was going to happen. So let's take a look at that.
T10, Rutherford and his co-workers were studying the angles at which alpha particles were scattered as they passed through a thin gold foil. Most of the alpha particles passed through undeflected. However, a few were found to be scattered at large angles, some even back in the direction from which they had come. This meant that they had collided with an object much more massive than the alpha particles themselves, yet so small that only a few alpha particles encountered them. This atomic level view shows what is happening. Most of the atom is occupied by the low mass electrons. The nucleus is small and massive. When an alpha particle encounters a nucleus, it is scattered at a large angle.
So as we saw there in that animation, pretty much most of them, again, had no problem, which meant, again, they didn't really run into anything. So instead of really the atom being filled with all this positive charge all over, the idea was perhaps there's nothing really there. It's kind of empty space. But again, what accounts for all these guys bouncing off at these really large angles is that it had to hit something very, very positively charged and densely positively charged. So they found that most of them were undeflected, as was talked about there in the video. And then again, they sort of compared it to like shooting a gun at a piece of paper and the bullet coming back. So clearly having to hit something that was very, very densely positive. So what did this mean? They really had to sort of move away. And on the left here is what they thought was going to happen. Again, most of them kind of going through with some deflection. But what they saw was on the right, most went through undeflected, but with some really large deflections happening. So they had to really sort of abandon Thomson's model of the atom and go, well, that plum pudding model, not so correct, and come up with really a new sort of explanation about the atom. And they said that the atom is mostly empty space. And that's what accounted for, again, all of those alpha particles sailing through. That's essentially where all the electrons are hanging out, kind of in that empty space, kind of flying around the electron cloud, if you want to sort of think about it that way, is sort of where we have our electrons. They said that it had a very dense positive core, which they called the nucleus, and later found that protons are found in the nucleus, which are positively charged. And in like 1930s, neutrons were found to be there that have no charge. And the other major sort of difference between the Plum Pudding model and really the current model of the atom is that most of the mass is the nucleus. So unlike the Plum Pudding model where they said most of the mass was really the electrons, here most of the mass of the atom is actually going to be the nucleus. And we're going to talk about why in a couple of slides, why it's actually most of the mass of the atom. So you do need to know Rutherford's experiment, what was done. You also need to know what they thought was going to happen versus what actually did happen, and obviously how that affected the model of the atom to where really the current model of the atom, mostly empty space, dense positive core, which is our nucleus, has protons, electrons are out at some distance. Is there going to be an attraction between the nucleus, which is basically positively charged because of those protons, and our negatively charged electrons? There is going to be attraction, right? Because that's, again, the opposite attraction. So there is an attractive force between those two. It's really what keeps the electrons from, for example, just flying away. And by the way, electrons in that empty space does not travel in pretty circles or anything like that. They do travel pretty randomly about the nucleus. So they don't travel in pretty circles or anything like that. And as we will talk about, that attraction between the electrons and the positively charged nucleus is why in certain cases only certain electrons, for example, are involved in bonding and other electrons are not involved in bonding. There are certain electrons that are too close to the nucleus, held too tightly to really go anywhere or be involved in bonding. There's electrons in higher energy levels, which are actually further away from the nucleus and not held as tightly, which are allowed to sort of participate in bonding. So it does affect, what electrons, for example, may participate in something like bonding. Any questions on that there? So here's just a little table of some of the experiments we just talked about and sort of the major things that came out of it. It's a good little summary table of, most of the stuff that you do need to know. So speaking of protons and sort of their discovery, it was found that they are positively charged. They are in the nucleus, and they do have a mass of 1.67 pi 2 times 10 to the minus 24 grams. We'll talk about why it goes so far out here in just a second. But just to remind you, the electron was something like 9.09 times 10 to the minus 28 grams. And as you can know, hopefully this number here is a much larger number than the electron. It's about 1,800 times heavier or so than an electron. So a proton is actually much heavier than an electron. And that also sort of backs up the idea from Rutherford that most of the mass of the atom is made up of the nucleus. Since protons are in the nucleus and they're about 1,800 or so times heavier than any electron that's flying around, it would make sense that the nucleus is actually most of the mass of the atom. Any question on that there? Now, at this stage, when we think about the atom, a couple of things are sort of understood. The nucleus comprises most of the mass of the atom, but actually it occupies a very small volume. So even though it's pretty much the center of mass there in an atom, it's actually a very small volume of it, which accounts for why most of those alpha particles had no problem sailing through because it missed it, because it's kind of relatively small. You could think of like the atom as like the size of the Superdome or a really big football stadium. You ever been to the Superdome? It's a very big football stadium. You sit in the seats and you feel like you're falling over in the seats. That's how tall and big it is in there. But it's like a very big football stadium, and like a marble on the 50-yard line. It's like the sort of nucleus. So a lot of empty space for those electrons to fly around in. Very small sort of center. that is very positively charged because of those protons that are confined to it. Now, the neutron, there's always sort of a belief that in addition to protons and electrons, there was another sort of particle, and also a belief that that particle was also found in the nucleus. And it wasn't until about 1932 that it was sort of discovered by a guy named Chadwick. He did a lot of experiments with beryllium and alpha particles, and he saw that a lot of particles that resembled gamma rays, so if you remember, gamma rays have no charge, were found sort of coming off. So he basically called these guys neutrons, and they're also found in the nucleus. And in addition, it has a 4 or 5 times 10 to the minus 24, and that's why they come out to so many digits between this one and the proton, and it's because that it's barely beats out the is the lightest of those 3 subatomic particles. So once again, this also sort of backs up the idea that it is the nucleus that is sort of the center of mass for an atom, because inside the nucleus, you have both the proton and the neutron, and they are both each about 1,800 or so times heavier than any electron that's flying around. So that would make sense that most of the mass is really that nucleus. So once again, nucleus, we have our protons positively charged, neutrons no charge, and out and about, kind of floating around in that empty space, is our electrons. Any questions on that? For us in here, you do not need to know the exact masses of each of these. I can't promise that they might not want you to know it as you continue on in your process. My guess would be yes, they probably do. But for us in here, you need to know, though, which one is the heaviest, which would be the neutron, which one's next, which would be the proton, and which one would be the lightest, which would be the electron. And obviously, you need to know their charges and where they are located in the atom. Any questions on that there? Here's sort of a summary of that table as well. So where they're all located, the modern version of the atom, obviously, which is what we've been talking about, empty space, nucleus, and all those type of things. Any questions on the atom? Okay. All right, so let's talk a little bit about some more parts of the atom. Here's sort of a cross section of what an atom sort of is. As you can see, we have a very small nucleus here, and kind of hard to see maybe on the screen, but there's sort of various shades of pink sort of happening as you go out to the end there. And this is what is sometimes referred to as an electron density map, and sort of the darker areas is a higher probability of finding electrons, and the lighter areas is a lower probability of finding electrons. As we'll talk about in a later chapter, I think 11, electrons, as I said, don't travel in pretty circles. They travel pretty randomly. And the best that you could ever do really is go, I think there's a high probability of finding electrons somewhere in the atom here. I don't really know where it is. I don't know how it's traveling, but there's a pretty high probability of finding an electron here versus, say, somewhere else. As you would imagine, since the nucleus is there in the middle and positively charged, there would be a pretty high probability near it. And as you would fan out away from the nucleus, the probability would go down. Doesn't mean you can't find an electron out there, but there'd be a less of a probability of finding it. So when we talk about atoms, though, pretty much most of its chemistry does come from electrons, because that's pretty much what's involved in bonds. And if you think about sort of the structure of an atom, electrons are on the outside, which means when atoms come together, they're pretty much the first ones to say hello to each other. And that's what's going to happen when things basically go through bonding, is those electrons. And as I mentioned before, it's really the valence electrons, which are those highest energy electrons that are involved in bonding, because they're not held as tightly to the nucleus. So that allows both ionic bonding to occur and covalent bonding, where we have either a transfer of electrons or sharing of electrons in each of those types of bonding. So let's talk about some other important areas of atoms: the atomic number, mass number, and isotopes. We're going to start with the atomic number. The atomic number, which is sometimes abbreviated with a Z, is the number of protons there are in the nucleus of an atom. Now, obviously, if we have a neutral atom, and since we only have 3 particles in an atom, we have protons, which are positively charged. We have electrons, which are negatively charged. And we have neutrons, which have no charge. It's really just these two guys that affect something, whether or not they have a charge or not. And if it's neutral, that would mean we need to have an equal number of those things, right? So if we have a certain number of positive protons, the only way to get neutral is to have an equal number of electrons. So if you are dealing with a neutral atom, the number of electrons will actually equal the atomic number. It is really important to know that if you're asked what is the definition of the atomic number, it is just the number of protons. So that is the actual definition. Sometimes people go proton. That is only protons. So don't mention in case you're asked that. But again, in a neutral atom, it will also tell you the number of electrons. Where can we find the atomic number? We go to our favorite thing, the periodic table there. And right there, that is the number up on top, is the atomic number. So if we look at nitrogen, which is the example we have there at the bottom, nitrogen has a lucky number 7 there. That means in a neutral nitrogen atom, we'll have 7 protons. And to match that, we would need 7 electrons, which gives us an overall charge of 0. So all the numbers that you see on either periodic table you look at, that's above the symbol. Those are the atomic numbers. When you look at those numbers on the periodic table, do any of the numbers repeat up on top? They do not repeat, which means every single element has its own atomic number, which means a couple of important aspects of an atom. If you know the number of protons, or you know the atomic number, which is essentially the same thing, you could just go to the periodic table and you know what element you're dealing with, because no other element will have the same atomic number or the same number of protons. Also, if you know what element you're dealing with, all you have to do is go to the periodic table, look at the number up on top, and you'll know how many protons there are. So with that piece of information, is it protons, electrons, or neutrons that's most important in terms of what element it is? Which one of those is most important? It is protons, right? That's why everybody has their own atomic number. That is why when we talk about a chemical reaction occurring, we have the same elements we started with and end with, because in a chemical reaction, it only deals with electrons. Nothing in the nucleus is touched. No protons in the nucleus is touched. And that's why if you start with 6 carbons in a chemical reaction, you will still end with 6 carbons on the other side, because nothing there in that nucleus, and specifically protons, are touched, and only the electrons are touched. So that's why we do have that conservation of elements. That's also why when we deal with like a nuclear reaction, for example, we don't have that, because a nuclear reaction does nothing more than do everything in the nucleus. It plays with protons, it plays with neutrons. You make protons, you remove protons, and that's why we don't have conservation of elements when you deal with nuclear reactions, which for your case, you won't see until 1B. But in Chem 1B, when you talk about nuclear reactions, you'll see that you do not have the conservation of elements like you do in a normal chemical reaction, like we talk about in this class, and also 1A. So that's a really important thing. You'll never have a nitrogen that has 5 protons, because 5 protons is boron. Yeah, number 5 up there. So boron is the guy with 5 protons, I guess. Any questions on that there? Another important number is the mass number, and the mass number is abbreviated as with an A. And the mass number is the number of protons and neutrons that you have in an atom's nucleus. Now, if we think about those two things, we have our mass number, which is our number of protons plus our number of neutrons. We have our atomic number that we just talked about, which is our number of protons. If we subtract those two things, if we take the mass number minus the atomic number, protons cancel and leaves us the number of neutrons. So if you know the mass number and you subtract it from the atomic number, you'll be able to figure out the number of neutrons there are in that particular atom. Except for hydrogen, which by the way has one proton, has one electron, has no neutrons. Everybody else has protons, electrons, and neutrons. So hydrogen only has a proton and an electron, does not have a neutron. So that's something you should definitely keep in mind. When you calculate these things, and another really important thing is when you calculate the mass number, the atomic number, the number of protons, electrons, and neutrons, they all should be positive whole numbers. So that brings up the double jeopardy question of my periodic table has more numbers on it, like something like this for hydrogen. Well, we know that's the atomic number. Is the bottom number the mass number? Can you find the mass number on the periodic table? The answer is no, that is not the mass number, right? So that is actually not the mass number. The reason we know that's not the mass number is pretty much this. They all need to be whole numbers. So if you look at the periodic table, all the numbers that come underneath the symbol, that's the easy way to remember it is not whole numbers, pretty much all of them, yeah? So don't be the person that writes that for the mass number. It always happens. Don't come ask me, should I use the mass numbers on the periodic table versus what's in the problem? Use what's in the problem, yeah? So you'll have enough information in the problem to properly calculate things like how many protons, electrons, and neutrons there are, the mass number, and the atomic number. You should never use the bottom number as the mass number. So really the only thing that you can find on the periodic table is the atomic number. So that's the only one that you can find up there. The reason it's sometimes confusing for people is when you go to calculate something like the mass number, a lot of times it's a number very close to the atomic mass. And people just think, well, they must have just like rounded or something. And that's not really the case. So if you have a question like this where you're asked to do protons, electrons, neutrons, atomic number, mass number, just go by the definition what those things are. And from the problem, you should have enough information to calculate anything that you would need to calculate outside of the atomic number, which you can find on the periodic table. Any questions on that there? So what are isotopes? Well, isotopes are, as I mentioned earlier, really the same element, but they have different masses. So in order for them to be the same element, as we just talked about, which particle has to be the same in all of them? The number of protons, right? So they all have the same number of protons, which makes them the same element because they all have the same atomic number. But what gives them different masses is they will have different numbers of neutrons. So because they have different numbers of neutrons, they will have different masses. And that's the one violation of Dalton's atomic theory, which is they are the same element, but their atoms are not identical because these isotopes have different numbers of neutrons. An example is hydrogen. Hydrogen has one proton, no neutrons. Deuterium, which is sometimes referred to as heavy hydrogen, has one proton and one neutron. And tritium, which is like the radioactive version of hydrogen, has one proton and two neutrons. So a very common way that we write isotopes with their mass number and atomic number is we use the symbol, and top left we put the mass number, bottom left there we put the atomic number. So if we were going to do this for each of these things, we would want to use a periodic table. Perhaps it would be your best friend probably when you're doing something like this. So we would see it has one proton, and that's the atomic number, which means what I would want to do is go to the periodic table and find number one, and I see that it is hydrogen in case I didn't know it was hydrogen. And that is the symbol I should use. It has one proton, which is the atomic number, which should go on the bottom. Its mass number would be the protons plus the neutrons in this case, which is one, and that would go up on top. And that would be the proper sort of symbol for our mass number, which is up here, and our atomic number, which is over here. Now we get to something like deuterium, and that really doesn't scream hydrogen to you, that name, does it? So it doesn't really sound like hydrogen. But if you were told it has one proton, I know from the periodic table, the only person that has one proton is actually hydrogen. So that is still hydrogen. And we would still use the hydrogen symbol. And I know it has still one proton, which means it should have an atomic number of 1 on the bottom left. And in this case, the mass number will be our protons, which is 1, and our neutrons, which is 1, which is 2 in this case. And 2 would come up on top there. And that would be the proper symbol there for deuterium, which even though it has a different name, is still hydrogen because it still has 1 proton. So isotopes sometimes have different names because of some properties. Now we get to tritium, which once again doesn't really scream hydrogen to you. But when it says 1 proton, I go to my periodic table. Again, I see number 1 is still hydrogen. And the atomic number is 1. Here we will do a mass number of 1 plus 2, which is 3 for our mass number. And that would go up on top. And that would be our symbol there for tritium. So although they all three have different names technically, hydrogen, deuterium, and tritium, they are all the same elements because they all have the same number of protons. They're all isotopes of each other because they all have different numbers of neutrons. And by the way, as you can see, you take the top number minus the bottom number, and that will give you the number of neutrons, right? So in this case, 1 minus 1 is 0. 2 minus 1 is 1. 3 minus 1 is 2. So we take the mass number, which is the top number, minus the bottom number. That will tell you how many neutrons there are. Question on that. So this is a common way that people will write isotopes. Another common way that you sometimes will see isotopes written is like, say, something like Cu64. So Cu is copper, 64 is what that's referred to. The 64 would be what number you think? Atomic number, mass number? If you're not sure, we could go to the periodic table, right? And we would look at copper. And when I look at copper above copper, I see number 29. It would be the mass number in this case, right? Because we know for sure if we go to the periodic table, the atomic number is 29. So this is a very common way isotopes are sometimes written as well. And that number does represent the mass number. And if we kind of were going to turn it into the other form, we would go with the copper. And from the periodic table, we know 29. And up on top would be 64. This means that copper here would have how many protons? 29, right? The atomic number. It is neutral. By the way, I know it's neutral because I see nothing written there. That's where a charge would normally be written. And if you don't see anything, you can assume it's neutral. That means the number of electrons in this case would be? It would be 29 as well, right? 29 positives, 29 negatives, give you no charge overall. Number of neutrons in this case would be 64 minus 29. Feels like a lot. 35 maybe. I'm going to try it without the calculators. Hopefully I did not too bad. But that will be 35 in this particular case. Any questions on that there? All right, so why don't we try some here, see what we got going on. I think maybe. All right, so for each of these, figure out how many protons, electrons, and neutrons there are in each of these guys here. Okay, so let's take a look. So once again, we got CO, which is cobalt. Again, the top number here is our mass number, which is our protons and neutrons. Bottom number there is our atomic number, which is our protons. So we know, hopefully off the bat here, that the number of protons in this case should be 27, which is our atomic number. We also, once again, see nothing written here, which implies that it is a neutral atom in this case, which means since the electrons are the only negative thing present, in order to get to no charge, we would need an equal number there of negative charges, right, to balance it out. And now for our number of neutrons, we take our mass number, which is 60, minus our atomic number, which is 27. So about 33 neutrons in this case. Any questions on that one there? Cl is chlorine. So once again, mass number up here, atomic number there on the bottom. So this again is a neutral guy, nothing written. So our protons would be 17 in this case. Once again, we would need an equal number of negatively charged electrons since we have no charge. And lastly, here our number of neutrons going to be 37 minus 17. That's like a 20, I think, in that case. Any questions on that one there? Down here, U is uranium, atomic number on the bottom, mass number up on top. So it is the atomic number, that's our protons, which is 92. Once again, no charge happening there, so equal number of electrons. And our number of neutrons here going to be our mass number of 238 minus our atomic number of 92. That feels like a lot, like a 146 and stuff. Any questions on any of those there? Okay. Let's try a couple more here. All right, so for each of these, write the symbol with the mass number and atomic number for each of these guys. Okay, so let's take a look. We'll start with krypton. So obviously periodic table here would be quite helpful. We go to periodic table and we find krypton, which is Kr. I think it's a 36 there above it. So that 36 is important because that tells us, right, our atomic number, right, which is also our number of protons. So we would have our Kr, we would put our 36 down there. Once again, that is our atomic number, which tells us our number of protons is 36. We are given the number of neutrons here, which is 48. So we'll take our 36 plus our 48, going to give us 84, looks like, when we add them together. And that's going to equal our mass number, right? And that would go up here, up on top in this case. Clearly, we could assume it's neutral because it didn't say anything about a charge or anything like that. So you can assume it as neutral. Any questions on that one there? Looking at the next one, which is nitrogen. So once again, going to the periodic table, we find N, which is nitrogen. We find our number up on top, which is 7, which is its atomic number. So once again, that's going to be our number of protons. So we'll go with N and a 7. Our number of protons here using our atomic number. And once again, our neutrons are given to us, which is 6. So that's going to be 13 when we add it together to get to the mass number. And that would go up on top. Any questions on that particular one there? Lastly, it's iron here, just right there, number 26 up there on the periodic table. And here we're actually given the mass number. So to write our symbol here, it would be 56 and 26 there on the bottom. They also wanted the number of protons, electrons, and neutrons in this case. So our number of protons, which would be our atomic number, which would be 26. Once again, it's neutral here, so our number of electrons should match. And once again, that gives us 0 for the overall charge. And lastly here, our number of neutrons would be our mass number minus our atomic number, and that's looking like a 30 pack right about there, yeah. Any questions on that there? Questions on protons, electrons, neutrons for things that are neutral. We'll talk about things with charges, obviously, just a sec. All right, I think it's a good place to lay it up for to talk about